this example, we have two 10 centimeter long parallel wires. That's these two parts. They're separated by 5 millimeters from here to here. What value of resistance, R, will give us a force between those two wires of 5.4 times 10 to the minus 5 newtons? Okay, so what's happening in this circuit is there are batteries in each branch of the circuit. The battery in this branch puts a current up here along this way. Let's call this one side 1. So this will be our current I1. And the current comes along here, down here, and around here, and so on. So there are 4 straight segments to this circuit. What happens? What magnetic field does that make? Okay, so let's do the top first. Along the top, this makes a magnetic field, big circles around the wire, and we're asking for what's the force on this loop, so we care what's the magnetic field here. This loop of wire makes magnetic fields around this loop of wire. It doesn't make any field right here. Same thing is true down here. This one makes loops of magnetic field around this wire, which doesn't make any field here. This branch of the circuit, this has a current that points up and makes magnetic fields that point this way, but this branch is really far away from this piece of the wire, so we're going to say that this part of the magnetic field is really small compared to this part, so that leaves us with this one. So this branch makes a magnetic field. It's big circles, so let's try and draw some of those circles on there. Circles come around here. We can get the orientation of the circles with our right hand rule. Our thumb goes with the wire. That's the dog chasing the cat, sorry. The thumb goes with the current, and your fingers on this side are going into the page, and on this side are coming back up out of the page. So right here, the magnetic field made by this piece of the wire where the current points down is pointing straight up. There's B1. So, can we find B1? Let's see if we can calculate B1. So B1 is the magnetic field made by this length of the wire. B1 has a magnitude of mu naught times I1 over 2 pi r. Mu naught is 4 pi times 10 to the minus 7 Teslas meters over amps, multiplied by current I1. Well, there's something we don't know just yet. Can we find current I1? Well, Ohm's law says that V equals IR, so then I is going to be V divided by R. The V is the potential, 9 volts, divided by the resistance, 2 ohms, gives us a current of 4.5 amps. And what about R? Do we know that guy? R is the distance between the two wires. R is 5 millimeters, or 5 times 10 to the minus 3 meters. So we'll put those numbers in. Divided by 2 times pi times 5 times 10 to the minus 3 meters. And what we get for our magnetic field is the magnitude is 1.8 times 10 to the minus 4 Teslas. For the direction of the magnetic field, we see that it's pointing out of the page. So if we take X, Y, and Z the usual way, out of the page would correspond with Z. So B1 is this magnitude with the direction of out of the page. Okay, so there's the size of the magnetic field. This is a current carrying wire. So this current carrying wire is going to feel a force due to this magnetic field. So let's write down what that force would be equal to. So the magnetic force on wire 2 is current 2 times the length of the wire. We see in the picture that that's 10 centimeters, crossed with the magnetic field that it's sitting in. So I2 times L. L is the length of the wire, 0.10 meters. It is a vector. It's the same direction as the current. So what's the direction of the current? Comes out of the positive and goes around the loop. So it comes to the left here, goes down here. Right off the bat, this is what we looked at in the last video. We have 2 current carrying wires with the current in the same direction. we expect there's going to be an attractive force between those two. So the direction of the current is down. Down corresponds to minus j hat. That's crossed with magnetic field B1 that we just found up above. We multiply all our constants out front. We get minus 1.8 times 10 to the minus 5. Those units are Teslas times meters, times I2, because we don't know I2, J cross K, and J cross K is equal to I. So then our force 2, I'm running out of space here, I'll go down onto another sheet. Our force F2 is equal to minus 1.8 times 10 to the minus 5 Teslas times meters times I2, and that direction is negative I hat, or to the left. Okay, now what do we know? It asks for the value of the resistance to get a force of 5.4 times 10 to the minus 5 newtons. So the magnitude of the force, F2, is 1.8 times 10 to the minus 5 Teslas times meters, I2. And that's equal to the given value, 5.4 times 10 to the minus 5 newtons. We can solve this expression for I2. And what we get for our current I2 is that it's 3 amps. Well, that's information that's good to have. It wasn't what was asked. The question what was asked what is this value of the resistance R? We can find that using Ohm's law. So we know that V2 equals I2 times the resistance R. R is the potential V2 over I2. I2 is 3 amps. V2 is the potential across the resistor. All of the potential will go across the resistor, so it'll be 9 volts. Divided by our current, which was 3 amps. So our resistor has to be 3 ohms in order to get the required force.